Think of nothing. What do you see? You might imagine a vacuum, a region of the universe drained of all matter and radiation. But go further, try to think of a true nothing, an absolute nothing. This nothing is not just empty, but devoid of space and time themselves. Given our everyday experiences, this is hard to imagine, but we have often struggled with the concept of nothing. The biblical story of creation tells us that in the beginning, God created the heaven and the earth. But what existed before God's creation? In a moment before time, in a place before space, the Bible simply does not say. And indeed, our scientific theories and observations also tell us that our universe has not existed for eternity. They tell us that 14 billion years ago, it had a beginning, a fiery birth in a maelstrom of particles and energy, and it has been expanding and cooling ever since. So what came before? Cosmologists offer tantalizing possibilities. Maybe our universe was begotten from a previous existence, part of an endless cycle, or formed in the violent collision between two other universes. But perhaps the most unsettling answer of all is that our universe was born from nothing. And if that is the case, how does one get something from nothing? Is no electron as real as 1 or 2 when electric or magnetic fields are at zero? Are the fields still there? These might seem like strange questions to ask, but by the early 20th century, our notion of physical reality had become somewhat fuzzy. The rigid clockwork universe of Newton had been replaced. Einstein had turned space and time on their heads with his theory of relativity, and experiments showed that the world of the very small was governed by a totally new set of physical laws in the world of atoms and electrons. Physicists spoke not of certainties but of probabilities, governed by brand new rules, the mathematics of quantum mechanics. But this is not how we see the world. Our macroscopic, large-scale world is one ruled by certainties, by things, by reason and logic. Nothing is nothing, something is something, and when you put your cup of coffee on the table, it stays there every time. Yet the distant world of the very small, the world of quantum strangeness, in which something can be born out of nothing and matter can pass through matter, has more of an effect on us and the entire universe than we might think. To understand this, we are going to go on a journey across time and space, from the universe's first moments to its far-flung future. We are going to unpack the meaning of quantum mechanics, explore its impact on the cosmos around us, leading us to the biggest question of all: just where did the universe come from? Werner Heisenberg had a nasty case of hay fever. As a young physicist, he had been trying to understand the rapidly changing landscape of early 20th century physics. For months, he'd been attempting to piece together the seemingly nonsensical world of the atom. He understood that in an atom, electrons orbit a nucleus. But if these orbits were like planets orbiting the sun, the atom would collapse in a fraction of a second and simply cease to exist. So what rules governed the motion of electrons? Everything he had tried failed as his mathematics became unwieldy and unruly. And now, his summer hay fever had hit. His head was becoming cloudy, his nose stuffy. He decided to escape, seeking sanctuary on the small island of Heligoland, located in the North Sea. He hoped the fresh, salty air would clear his mind. And it was on tiny, isolated Heligoland, while relaxing one evening, that he was hit by a revelation that totally changed our understanding of reality. It had all begun in 1900 with Max Planck's desperate attempts to explain how hot objects glow. He knew that in hot objects, atoms jiggled, and it was this jiggling that produced the rainbow of colors he could see. In classical physics, all possible jiggles were allowed. But to agree with experiments, Planck added a new, unexpected ingredient. He restricted the jiggles so energies were present in distinct individual chunks, and in quantizing these jiggles, quantum mechanics was born. By the 1920s, this world of the very small, the world of atoms and electrons, had become a strange and complex place. Just like energy, the orbits of electrons appear to be quantized too, existing at specific distances from the nucleus. In 1925, Erwin Schrödinger wrote down his wave equation to explain quantum mechanics. Objects like electrons were no longer in a particular place. Instead, they were fuzzy and spread out. Described by something known as a wave function, Heisenberg had been caught up in this swirling, heady mix of quantum theory. Like others, he was trying to bend well-established rules to explain how electrons orbited in atoms. Perhaps they underwent a little oscillation, something Heisenberg knew how to calculate. However, like all the attempts before him, his calculations failed to explain what the experimenters were telling him. But in the cool, fresh sea air of Heligoland, new ideas quickly crystallized. He realized that we can never actually observe an electron in its orbit. What we see are the emitted frequencies of light as electrons move from one orbit to another. So why bother trying to calculate the details of the orbit, he decided. What we should calculate is what we can actually observe in our experiments. Heisenberg began working through the mathematics, ignoring how the electron was precisely moving, and it was then things came into stark clarity. His new mathematics worked. The form of the equations in front of him seemed strange, but a mathematician would have recognized them as matrices. While these are common in physics today, there was still novelty in the 1920s. Heisenberg did not sleep that night. Instead, he set off on a pre-dawn walk. He sat and watched the first rays of the sun peek over the horizon from a rocky outcrop on the island. As the day warmed, he realized he had a new mathematical way of explaining the world of the very small. But what a bizarre world he had found. Heisenberg's mathematics tallied with Schrödinger's. They did not talk of where an electron is, only where it might be. And when it came to an electron's speed, the description was equally vague. How an electron jumps from one orbit to the next was unknowable, just the energy emitted when it did so. And it didn't talk about the precise time the electron would make such a quantum jump, just the chances of the jump occurring. The quantum world was not a work of precision. The quantum world was one of probabilities. Staring at his equations, Heisenberg realized the vagueness in position and speed were, in fact, related. He saw that the more accurately we can discern the position, the less certain we are of speed, and if we try to accurately determine speed, the position is fuzzier. Imagine you put an electron in a tiny box. In the classical world, the electron would happily rattle around, bouncing off the walls. If you cool the electron, it will move slower and slower. Eventually, you can cool the electron to absolute zero, and it would sit at rest, not moving. But Heisenberg's uncertainty principle means that in quantum mechanics, this is strictly forbidden. As we know where the electron is confined within the walls of the box, there is a fuzzy limit to what we can know of its speed. No matter what we do, quantum physics prevents us from cooling an electron down to absolute zero. Try as we might, there will always be some residual jiggling. On top of this, like position and velocity, energy and time are not precise things in quantum physics. And like position and velocity, how well you can determine one is related to how you determine the other. The energy of things can fluctuate over time, with small quantities appearing and disappearing on tiny time scales, very briefly breaking the law of conservation of energy. This means that even empty space jiggles, a residual energy in the vacuum that is always there, known as the quantum vacuum. This fills the entire universe as virtual particles flicker in and out of existence. So in the quantum world, empty space is not really empty. Nothing, it turns out, is something. Heisenberg's uncertainty principle is a fundamental law of the universe, and yet it seems disconnected from our large-scale reality. But as we will see on the next stage of our journey, the physics of the very tiny does have big implications for the cosmos, from our very existence to the birth of the universe itself. To understand quantum mechanics' role in the universe, we are going to have to think about our sun. For many years of human history, the sun was a god to the ancient Egyptians. The sun was Ra, king of all gods and father of creation. To the Greeks, he was Helios, who rode his chariot daily across the sky. But what powered the sun? Was it just a flaming ball like the fires on Earth? It wasn't until the mid-1800s that science started to provide answers. And it started with Lord Kelvin, the determiner of absolute zero, and after whom the units of temperature are named. He was considering just how old the sun was. With the physics of the day, Kelvin deduced that our star was an immense ball of hot gas squeezed to high temperatures by its gravity, and there was only so much mass in the sun to maintain it. It seems on the whole most probable that the sun has not illuminated the Earth for 100 million years, and almost certain that he has not done so for 500 million years. As for the future, we may say with equal certainty that inhabitants of the Earth cannot continue to enjoy the light and heat essential to their life for many millions of years longer, unless sources now unknown to us are prepared in the great storehouse of creation. This estimate dismayed geologists and biologists. It simply left too little time for the weathering of continents or the evolution of animals. But Lord Kelvin did not know about the physics of the nucleus. By the 20th century, physicists had realized that atoms had a definite structure. The negatively charged electrons orbit a nucleus composed of positive protons and neutral neutrons. But the atomic nucleus is tiny, thousands of times smaller than the atom itself, so an immense force must be present to counter the mutual repulsion of protons crammed into the tiny nuclear volume. Unimaginatively, physicists call this the strong force, and if this force could be tapped in nuclear reactions, energy would be unleashed. Soon, experimenters were crushing atoms together and outpoured copious energy. Eventually, in 1920, Cambridge astronomer Arthur Eddington put two and two together. He decided the power of stars lay within the nuclei of atoms. Stars, including our sun, are mainly hydrogen, the simplest element in the cosmos. Throughout the 1930s, physicists realized that starlight must be generated by nuclear fusion. This is when lighter elements like hydrogen are bound together by the strong force into heavier elements. But just how did this work? There were clearly two forces to worry about. Firstly, the strong force responsible for binding the nuclei together. But the strong force only acts over very short distances. Two nuclei must essentially touch for the strong force to latch them together. As the nuclei are composed of positively charged protons, they repel through electromagnetism. For fusion to work in the sun, nuclei must be thrown together hard enough to overcome the electromagnetic repulsion and for the strong force to grab on. But there is a problem. The core of a star is crushed to incredibly high temperatures by the weight of the star pressing down. Astronomers have calculated a newborn sun would have a central temperature approaching 15 million kelvins. But at this temperature, the collisions between protons, the nuclei of hydrogen, are just too gentle. The electromagnetic repulsion keeps the protons too far apart for fusion. So how could the sun possibly shine? And this is where the tiny quantum world comes in. The answer was given by an enigmatic scientist, George Gamow, born in Odessa. When it was part of the Russian Empire, Gamow was a true polymath. His mind roamed from the birth of the universe, through radioactivity, and into how DNA stored information. But for our story, it is Gamow's insight into quantum mechanics that matters. He realized that we cannot treat colliding nuclei like solid balls of matter due to Heisenberg's uncertainty principle. At the quantum level, everything is fuzzy. When two nuclei collide, they are not simply a certain distance apart. They are many distances apart instantaneously. And somewhere in this fuzzy mix, they might be close enough for the strong force to do its work. Through quantum uncertainty, the two nuclei overcome the barrier of electromagnetic repulsion, allowing them to fuse and release their nuclear energy. This tunneling through such seemingly impenetrable barriers is a feature of the quantum world, and it is this that allows the sun to shine. Following these revelations throughout the 40s and 50s, astronomers steadily uncovered the secret lives of stars, spurred on by the surge in nuclear research throughout the Second World War. They pieced together the complex web of nuclear burning, firstly from simple hydrogen into helium, then helium into beryllium and carbon, and then onto heavier elements. But even with the help of quantum physics, nuclear reactions are fickle. Very massive stars are needed to create heavier elements from carbon and oxygen and up to iron. It is only in their cores, crushed to immense temperatures and density by their weight, can the extreme conditions needed for this nuclear burning occur. These elements are essential for our existence in the universe. But of course, they are useless, locked away, buried deep within stars. It is only at the end of a star's life that elements can be released, and just as the seemingly tiny, macroscopically irrelevant world of quantum mechanics gives them light, it can propel these elements into the cosmos in spectacular fashion. The neutrino is a curious particle with virtually no mass and no charge, and so is invisible to all electric and magnetic fields. It is also blind to the strong force that binds the nuclei of atoms together. In fact, neutrinos only feel the weak force, the strangest of all the fundamental quantum forces posited by Wolfgang Pauli in the 1930s. Due to their incredible elusiveness, it wouldn't be another 25 years until neutrinos were finally captured in an experiment. This is because, with only quantum weak force interactions, the neutrino simply ignores most matter. It will happily travel through a light year of lead before there's a chance of it interacting with a single atom. And yet, they play a crucial role in supernova, the death of massive stars. In the immense crush of a collapsing giant star, electrons are forced into protons, and this radioactive decay spits out neutrinos. Huge numbers of neutrinos try to escape the star, but, finding themselves in a super-dense environment, they slam into the infalling layers. And by sheer numbers, they reverse the collapse and rip the star apart, spewing the diverse elements back into the cosmos. Clearly, quantum physics is written into the operation of the universe. Through its role in generating solar heat or recycling elements across the cosmos, it is essential for our every existence. But it doesn't stop there. Could quantum physics play an even larger role? Do we only need to think about the quantum nature of the extremely tiny, or is there a bigger question we should be asking? Is the entire universe a quantum object? In quantum physics, the wave function encapsulates all the information in an object. But two individual objects are not described by two individual wave functions. Instead, we use a single wave function to encompass both. In fact, in quantum theory, we can use a single wave function to describe any number of particles. This raises a huge question, one of the biggest possible. Could we write down a single wave function to account for the quantum state of the entire universe? A wave function to account for every particle of matter and photon of light. It would be truly immense, but at the very least, theoretically possible. Consider the world of classical physics. Imagine you could know the precise location and speed of every atom and photon at a particular instant. Impractical but possible in theory. With this information, you could use the laws of physics to calculate where every particle will be in the future. This is because classical physics is deterministic, and with it, the universe ticks like clockwork. The future is completely written into the fabric of today. Quantum physics, on the other hand, is built on probabilities. Knowing the wave function today will tell me the wave function tomorrow, but not a single definite tomorrow, a whole host of possible tomorrows. Which of these follows the true future path of the universe? Physicists are unsure, and in the 1950s, Hugh Everett IE proposed a radical solution. In his many worlds viewpoint, he decided that there was no single future for the universe. Out there in this multiverse of universes, there are other versions of you. In some universes, you may have won the lottery. In others, you may be a rock star or a famous actor. And of course, in some, you are absolutely identical. Everett's ideas were too radical for the time and unappreciated. He eventually left science, but the notion of a wave function for the entire universe did not leave with him. Even Stephen Hawking pondered whether a quantum universe could solve one of the great mysteries, namely whether the universe had a beginning. Working with Jim Hartle, He deduced that in the early universe, the quantum nature of time was indistinct. With this, time only really came into existence when the universe became more distinct. The singularity that dogged classical cosmology written in relativity just didn't occur because there was no real time when it could have. As you can imagine, not everyone is happy with this picture, and debate continues to rage. And indeed, that is far from the only way quantum physics has been implicated in the beginning of our universe. To find out more, we must travel back in time, back to the first trillionth of a second of existence. Perhaps we will find that we are lost in the multiverse, just one universe of countless others. Or perhaps we will pry open the door to find ourselves staring into an abyss, an aberration born from a random fluctuation. Our existence, little more than a quantum dream against a backdrop of unending nothingness. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching. I will see you next time.